Hello guys, this is Edward from STEM. Today we are going to be looking at shapes of simple molecules and we're going to use the VSEPR theory. The VSEPR simply stands for valence shell electron pair repulsion. So that will help us to determine the shapes of simple molecules. And the shapes we're going to look at, we're going to be looking at the first one, the linear shape. Second one, we have bent or V-shaped, depending on your specification, or V-shaped. Some can call it angular as well. Okay. And the third shape is we have trigonal planar, trigonal planar. The third one we have triangular pyramidal, triangular pyramidal. And the fifth shape is we're going to look at tetrahedral, and the sixth one we're going to look at is trigonal bipyramidal. Okay, trigonal bipyramidal. And lastly, we're going to look at the octahedral shape. Okay, so but before we continue, if you haven't done so, kindly subscribe to my channel, like the videos. If you have any questions, drop them in the comment section, and do not forget to turn on your notification bell so that you get to be notified whenever a new video like this is dropped. Okay, so before we dive into the different shapes of molecules, it is important we understand how to determine the different shapes of molecules. And the shapes of molecules are basically determined by the number of paired electrons around the central atom. All right, now this is what I mean. Let's say we have a central atom X, all right, and this central atom is bonded with other atoms. Let's say A. Now this bond here represent paired bonded electrons, right? Now, the number of these paired bonded electrons determines the shape of molecules because naturally the paired bonded electrons exert force of repulsion between themselves to the maximum. Okay, so naturally they tend to experience maximum um, force of repulsion. Okay, so that determines the shape of molecule. Now, additionally, we know that there are some um, molecules that contains bonded electron and as well lone pair of electrons, right? So let's say we have center atom X, and this center atom X is bonded with A, all right? Some molecules has lone pair of electrons. So this lone pair of electron here also contributes to additional repulsion force. Okay, so that as well um, contribute to the shapes of molecules because it reduces the um, bond angle by 2.5 degree. Okay, we are going to see how that is applicable in different shapes of molecule in a jiffy. So to determine the shapes of molecules, there are a couple of things you need to take note of. The first thing you're going to take note of is to find the number of electrons pair. Okay, find the number of electron pairs. Number two, you are going to determine how many of the electron pairs are bonding and how many are lone pairs. Okay, so these are the things that you need to determine before you get to know the shapes of the molecules. And thirdly, have that in mind that the bonding pairs, okay, indicate the basic shape. The bonding pairs indicates the basic shape, while the lone pairs indicate additional repulsion. So you need to have this at the back of your mind. All right. So let's start with the first one, the first shape, linear shape. Okay. So the term linear is self-explanatory, right? So now in linear shape, there are usually two pairs of bonding electron. Okay, or should I say two bonding pairs of electron? So we have two bonding pairs of electron. Okay, and there is no lone pair of electron. Zero lone pair. Zero lone pairs of electron. All right, and the shape of this molecule is usually 180 degree. Of course, linear shape is 180 degree, right? Let's look at the example. Example can be found in CO2. CO2. Now in CO2, the central atom here is carbon, right? Right, and carbon is bonded with oxygen, and we have oxygen here as well. So the shape of this is 180 degree. I hope that makes sense. Another example, we can see that in beryllium chloride. Beryllium chloride. Okay, the center atom here is beryllium. Okay, beryllium. Then we have chlorine attached. All right. So also this is the bond angle here is 180 degree as well. I hope that makes sense. So let's look at V-shaped molecule. V-shaped or bent, depending on your specification. So in V-shaped molecules, there are usually two bonding pairs of electron, two bonding pairs, okay, of electrons, and two lone pairs of electrons. And two lone pairs of electrons. And the shape of these molecules are 104 degree, 104.5 degree. That can be found in water, H2O. In water, the center atom is oxygen, right? Now, remember we said that it contains two bonding pairs and two lone pairs. Now, let's say, for example, let's assume that there is no lone pairs, okay? If there is no lone pairs, you will expect that it will be linear, right? Now, I want to show you the effect of lone pairs, right? So now, if there is no lone pairs, you will expect to have something like this, okay? Something like this, all right? Now, but because of the presence of lone pairs, see what happened? The lone pair here will cause additional repulsion that will make this bond to extend. Okay, remember it's two lone pairs. Then we also have another lone pairs here. This second lone pair will also cause this bond to extend because of force of repulsion. So in this case, we are going to have a bent or V-shaped V-shaped molecule. So water then becomes, we have center atoms of oxygen, and we have bonded with hydrogen, two bonded with hydrogen, and 2 lone pairs of electrons. Okay, I hope that makes sense. And the angle is 104.5 degree. Later on, I'll explain how it is 104.5 degree. Okay, I hope that makes sense. Now, some people usually make mistake. They tend to put the lone pairs of electron below. Okay, some people tend to draw the shape like this. They put the lone pairs of electron like this. No, this is wrong. Okay, this is wrong. All right. Now, another example of V-shaped molecule is SO2. Okay, in SO2, the sulfur is the center atom S. Right? Now, it is bonded with oxygen. Okay, on one side and oxygen on the other side. So this oxygen here has 2 lone pairs, okay, because of the double bond, while the oxygen here has 3 lone pairs because of the single bond. So that is not what we are interested in, but anyway, you are interested in the center atom S. Now, notice here that the sulfur here has just 1 lone pairs of electron, but the angle here is less than 120. Sorry, less than. This should be less than 120 degree. Okay, so this is also another example of a V-shaped molecule. The other shape you're going to look at is trigonal planar. Trigonal planar shape. Now, the word tri means what? Means 3. Okay, so it means 3. So basically, it means that there are 3 bonded electrons. What planar means? What? It is flat. Okay, it is flat. So let's see how the properties of this shape. Now, trigonal has 3 bonded electrons. Okay, and it has 0 lone pair. So it has no lone pair. Okay, and the shape of these molecules are usually 120 degree. So we'll see how it is 120 degree. Example of this shape can be seen in boron fluoride. Okay, boron fluoride. So in boron fluoride, boron is the center atom, right? And this center atom is bonded with 3 fluorine atoms, right? And there is no lone pair of electron, right? So now, if you have a shape like this, and we know that this is like a 360 degree, right? Now 360 degree, and we have 3 bonded electrons. 360 divided by 3, and that will give us 120, right? So this bond angle here is equal to 120 degree. Now, provided that there is no double bond, okay? So it's 120 degree. All right. So let's look at another example, another shape. So let's look at another shape, angular pyramid. Now, as the term implies, triangular, tries also means that it contains 3, okay, like 3 bonded electrons, right? But the pyramid here indicates that it is not flat. It contains additional lone pair of electrons. In triangular pyramid, we have, okay, 3 bonded pairs of electrons and one lone pair one lone pairs of electrons, and the shape is 107 degree. The shape is about 107 degree. All right, now example of such molecule can be of such shape can be found in ammonia and H3. Ammonia. Now ammonia has center atom nitrogen, right? And right now nitrogen is bonded with three hydrogen atoms. Okay. And in case you're wondering, I'm sure you know how to determine this by now. Okay. But if you're wondering, now nitrogen has the valence of nitrogen is 5, right? 1, 2, 3, 4, 5, right? So now this 3 is bonded with this one is bonded with hydrogen, this one too is bonded with hydrogen, and this one too is bonded with hydrogen. So we have these two that is not bonded with anything. That is lone pair. All right. So that is what I am describing here. Right. So now the nitrogen also has one lone pair of electrons. Okay, you think that this is trigonal, so it's going to be 120, but no, it's not 120 because of the presence of this lone pair of electron here. All right, so the angle becomes 107 degree. All right, I hope that makes sense. Now, other examples of molecules that has this trigonal pyramidal shape are after ammonia, we have phosphine or phosphorus trihydride. We also have arsenine trihydride, right? Now, some of you will be wondering, how can we then differentiate between trigonal pyramidal and trigonal planar? Now, I will leave you with a clue on how to easily differentiate between these two shapes. All right. Now, if you take a look at trigonal pyramidal, all the center atoms, right, are found in group 5A of the periodic table. Okay. Why for trigonal planar examples, we have boron hydride, we have aluminum chloride. Now, all the center atoms are found in group 3A of the periodic table. And I hope that makes sense. So another shape we are going to look at is tetrahedral. Okay, and from the prefix tetra, it shows that it has 4 bonding pairs of electrons. Pairs of electrons, and it has 0 lone pairs of electrons. Right, and the bond angle is usually 109.5 degree. Example of a molecule with tetrahedral shape can be found in, or example is methane CH4. Okay, so now one would expect that if it's CH4, one would expect that the shape, the molecular shape should be in this form. Okay, you expect that it to be bonded this way, but this is not how it's bonded, because if it's bonded this way, the bond angle should be 90 degree. Okay, but that is not how it's bonded. Now the center atom is carbon, right? And the carbon is bonded with hydrogen. Okay, then you have hydrogen, hydrogen, and then hydrogen. So this is the actual shape of methane, and that gives the bond angle of 109.5 degree. Another example can be found in silicon fluoride. Silicon fluoride. So in silicon fluoride, silicon is the center atom S, and is bonded with 4 fluorine atoms. Fluorine, fluorine, and fluorine. Just as we can see in methane, okay, the bond angle as well is 109.5 degree. So let's look at another shape called trigonal bipyramidal. Bipyramidal. Okay, now this shape has 5 bonding pairs of electrons. Okay, and it has 0 lone pairs of electrons. 0 lone pairs of electrons. The shapes are usually 90 degree and 120 degree. All right. Example can be seen in phosphorus pentachloride. Now let's draw the shape of this molecule. So in phosphorus pentachloride, the center atom is phosphorus P and is bonded with 5 chlorine atoms. So we have chlorine here, we have chlorine here, we have chlorine here, and we have chlorine here. So this is phosphorus pentachloride, and that is an example of trigonal bipyramidal molecular shape. So the last shape we're going to look at is octahedral. Octahedral. Now in octahedral, the central atom is bonded with 6 electrons. Okay, it has 6 bonding pairs of electrons. And it has 0 lone pairs of electrons. All right, the angle is usually 90 degree. Okay, example can be found in sulfur hexafluoride. Sulfur hexafluoride. Okay, so in this compound, sulfur is the central atom. We have central atom S is bonded with 6 fluoride atoms. We have fluorine, we have fluorine, 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 and fluorine. I'm sure you'll be wondering why is it called octahedral when it is actually bonded with 6 electrons. Now the thing is this, if you look at the shape of this molecule, if it's actually in a 3D form, okay? So if you draw it in a 3D form, it's going to have 8 sides. Okay, that's the reason why it is called octahedral. I promised to show you how lone pairs of electron affect the bond angle, right? Let's take methane for example. Methane is CH4, right? CH4. And this is tetrahedral. Right? And the bond angle here is 109.5 degree. Now, if you notice, in tetrahedral, the center atom C is bonded or has 4 things attached to it, right? 1, 2, 3, 4. Now take note of that. Now let's look at trigonal pyramidal. In trigonal pyramidal, we have, for example, ammonia. Ammonia also has 4 things attached to it. It has 3 hydrogens, right? And 1 lone pairs. So basically it has 4 things attached to it as well. Now, remember we said that the presence of lone pair of electrons reduces the bond angle by approximately 2.5 degree. Now look at how that will affect the bond angle of this trigonal pyramidal. This is trigonal pyramidal. Okay. Now since this is, you have 4 things attached to 1, 2, 3, 4, just like we have in tetrahedral, but the tetrahedral is 109.5, and because of this pair of electrons, this angle 109.5 will be reduced by 2.5, and that will give us 107 degree, and that is the angle of trigonal pyramidal. I hope that makes sense. Now let's look at water. Now water is example of a bent shape, right? Now we have in water, we have the center atom to be oxygen. Okay, oxygen, and oxygen it also has 4 things attached to it. It has 2 hydrogens attached to it, and it has 2 lone pairs of electrons. So basically it has 4 things attached to it. 1, 2, 3, 4. Now from 109, if it has four things attached to it, it's expected to have 109.5 as tetrahedral, right? But because of the 2 lone pairs of electron, and each lone pair of electron reduces the bond angle by 2.5. Okay, so if you have two lone pairs of electron, it's going to reduce the angle by what? By approximately 5 degree. So if you subtract 109.5 minus 5, that will give us 104.5 degree. Now, have you been able to see the correlation between how the lone pairs of electron affect the angles, the bond angles? Okay, so let's look at another one. Let's look at a trigonal planar. We have boron hydride. Now, boron hydride has 3 things attached to it. Right, 3 hydrogen attached to it. Right, and the bond angle is, like we said, is 120 degree. Yeah, and let's look at sulfur oxide, which is a bent. Okay, this is trigonal pyramidal. Sorry, this is trigonal planar rather. Trigonal planar. Let's look at bent, which is sulfur oxide. Right, we have sulfur oxide. In sulfur oxide, sulfur is the central atom, right? And it also has 3 things attached to it. It has 3 things attached to it. It has 2 oxygen and 1 lone pairs of electron. So basically it has 1, 2, 3 things attached to it. So since it has things attached to it, you expect that it has the bond angle be 120, right? No, but because of the pairs of electron, the bond angle will be reduced, right? And that will be less than 120 degree. So if you subtract 2.5 from 120 degree, you are going to have approximately 117.5 degree. I hope you have been able to understand how the lone pairs of electrons affect the bond angle. This was what I promised to explain at the end of the video. I hope that makes sense. Now, if you find this video useful, kindly subscribe to my channel, like the videos, share the videos. If you have any question, drop them in the comment section, and do not forget to turn on your notification bell so that you get notified whenever a new video like this is dropped. Thank you for watching.